Our next talk is from Terpol, and the topic is Terpol and the circularity of rubber in the automotive industry. Mr. Nasser will be the speaker. He is a chemist and business manager. He's the CEO of Prokitech and creator of the Terpol technology. Have a great talk. Thank you very much. Thank you. Good afternoon. Let's start our presentation of a new technology in which our main actor is natural rubber being used for this first time in plastic. And it's mostly dedicated to applications of the automotive industry. This Terpol project, the commercial name of this technology is Terpol, was supported by HyperNano. It's an incubator at Mackenzie University where we have engineers and state of the art equipment for our development, and with the Somchern plastic injectors that are partners in this project. Okay, what is Terpol? It's a thermoplastic made from natural rubber for the first time. And it's the greenest polymer that exists, and we're going to talk about it. It was turned into thermoplastic, and this thermoplastic allows parts to be produced, like Amaudi was saying, in rubber by extrusion or injection or plastic thermal molding, and it's 100% recyclable. It's completely compatible to all types of plastic, and we're also going to see circular economy, the mix of all these plastics and what we can develop, not needing to separate plastics in recycling. This is the main point. It connects several non-compatible plastics naturally through the natural rubber, and this opens the possibility for many things. It can combine polar and apolar resins, and in the automotive industry, at the end of the vehicle's life cycle, makes recycling easier and not being sent to the landfill, which is our main mission, not having plastic in the landfills anymore.
And providing elastomeric conditions to the plastic. So flexibility, soft touch that everybody's looking for. So a rubbery touch, so to speak. Flexibility, elasticity. Those are the properties of rubber on plastic. So, like I mentioned, it's a new disruptive concept, something that we've never seen before, which is using polyisoprene. And in the presentation, they were talking about TPV, PD, EPDM. Here we're talking about polyisoprene. So polyisoprene is the carbonic chain of natural rubber. It's one of the longest chains. I'm not going to go into the chemical details though. But imagine that it's an infinite chain. That's why it has high mechanical properties to make different parts, such as airplane tires. It's 100% natural rubber from the rubber tree. They cannot use synthetic rubber except for natural rubber. Truck tires, there's a blend, pretty much 50-50 in synthetic and natural rubber. And vehicles, you can use more synthetic instead of natural, depending on the manufacturer. Natural rubber has huge mechanical and dynamic properties. So when you start the engine, it's vibrating, right? And Marie can explain that to us with a lot of precision. So you need some buffers to decrease the vibration. So there's a lot of dynamic work. An elastic, for instance, that old type of rubber bands, those are natural rubber. Condoms are 100% natural rubber. Birthday balloons, 100% natural rubber. But all of those rubbers went through a vulcanization process. So what's the vulcanization process or cross-linking process? Vulcanization is with sulfur and cross-linking is peroxide, with peroxide. So when we transform a rubber from a gum to an elastic by adding sulfur or peroxide at high temperature, that's a cure process. And it goes from being a gum, and with temperature or sulfur or peroxide, it'll turn into an elastic and it won't go back again. A tire, you can grind it, use it as a charge somewhere, but most of them are burned because there's no recyclability, and that's one of the biggest challenges in the automotive industry, because after you vulcanized it won't go back. So here we propose to use natural rubber but completely recyclable because it wasn't cured. Terpol isn't cured. It doesn't have sulfur, it doesn't have peroxide. It's completely thermal. It's a thermoplastic product that's completely natural. So it gives us the environmental advantage over the other modifiers. So it will have elastomeric properties or plastic properties, as well as the possibility of producing, and I'll give you an example of that later, not auto parts, but it can also be used in auto parts. So parts that were injected with Terpol Pure, so you can feel the touch that we offer to injected products. It can be applied to the injection process, extrusion, thermoset, and even blown parts and 3D. Flexible 3D printing, because most of the 3D printing is rigid. And with Terpol, you can obtain filaments that are completely flexible and 100% circular and recyclable. So we created a prototype. So you grind all of Terpol, make it granulate, create a new filament, and print 3D again, any number of times you wish. So at the end of the day, we're talking about not creating a product that would go to a landfill and being circular. The Terpol dose as a plastic modifier changes a lot. It can go from 5 to 20%, depending on the applications that we're looking for. Why did we pick rubber from the rubber tree instead of EPDM or nitro rubber or any other rubbers for Terpol? Starting off with the environmental side. So the carbon footprint of SBR, which is the one that's most sold around the world. So sneaker soles, tires, and many other parts are produced in SBR. It's styrene butadiene rubber. So it's 5.75 footprint. So for each kilo produced, it generates 5.75 carbon emissions. EPDM is a little lower, 4.71. Polybutadiene is 6.12, much higher than plastics, for instance. In olefin, you have polyethylene, or polyethylene is approximately 2. The plastic that generates the most carbon is a polyester with 4 something, and natural rubber is 0.70. There's some that are 0.50. In Asia, natural rubber currently has FSC certification, and the carbon footprint is even lower. It's 0.04. So the date is here, and this is where we got the information. And that's why we picked it as our main player, the rubber tree rubber. This is our refinery. Our refinery is a tree. So when we talk about sustainability in polymers, there's nothing greener than natural rubber. This is called Hervia brasiliensis because its origin is in Brazil. And unfortunately, 120 years ago, Brazilians fought with the English in Manaus, in the Amazon. I'm not sure if you know, but Manaus, 120 or 140 years ago, was richer than Paris because rubber was gold. And that was the only place where we had gold. That's the only place where we had natural rubber. Because the automotive industry was just starting, and for mobility, the embargoes. Germany had no longer had access to rubber from the rubber tree, so they developed synthetic rubbers to provide for the lack of natural rubber. Otherwise, they could move the trucks and they would lose the war fast. You wouldn't have mobility in the war without the rubber. So the Brazilians fought with the English in that area of Manaus. So the English got the seeds of the natural rubber and went to Ecuador. Where do we have a colony? In Malaysia. So Malaysia is in the same line. They planted rubber trees there. And after a while, Malaysia became the biggest natural rubber producer in the world. It's no longer the biggest producer. Now it's a neighboring country, Thailand. Thailand is now responsible for 1/3 of all the natural rubber in the world. The consumption of natural rubber is 13 million tons per year. 70% goes to tires. And the rest, as I mentioned, condoms, birthday balloons, surgical gloves, and so on. So currently, 1/3 equals to 4 million tons in Thailand. So who produces the most? Who else? Vietnam, Indonesia, and Africa is coming in strong with the Ivory Coast and Nigeria, and they're also strong with the production of natural rubber. What about Brazil? Do you know what the percentage is of Brazil's production for the world? Guess. 5%. Approximately. Less than 5%. but less than 5% is less than 2, actually. 2% approximately of all of the natural rubber in the world. So what are the details of the main player? Why is it so green? One tree only produces 5 to 7 kilos of rubber per year, but the whole entire tree, the trunk, the leaves, and so on, absorbs 150 kilos of carbon on an annual basis. So it's a filter. You can call it a filter. Second, it's not competing with food. So everybody has their own technology, and all technologies have to be respected, and they all have their own applications. But I have to say that we don't use sugarcane or corn, which is food or a byproduct, and turn that to ethanol, to then turn it into ethylene, to then become polyethylene. In this case, it's ready to use. So we're not competing with foods at all. And you can also plant them together with foods. It generates green jobs. Imagine in Thailand how many jobs are generated in the fields in Thailand to produce the 3-4 million tons of natural rubber in the world. In Brazil, we have an area that's the size of France of degraded land that could be used to plant natural rubber. But what are they doing in Brazil? They're actually destroying plantations because they say it's not worth it. So it seems like they're going the wrong way, and the world needs natural rubber. So it does create green jobs, can be planted in a degraded land with rainwater. And most importantly, the forest is still standing. So we have products that are necessary for forests. We need forests for some products. So we need to plant trees for pulp to become paper. So you plant eucalyptus, in 7 years, it's ready to be cut to get pulp. What's going to happen to that? They knock it down. And when they do, there are animals there and birds and so on. So we lose all of that. Therefore, we have to be very careful with the currently available information because anybody can say anything. So be very careful when they're comparing technologies, paper technologies with plastics and so on, because everybody has to respect their own space. And São Paulo is famous for its pizza, right? Imagine ordering a pizza in plastic packaging. That wouldn't work. Instead of paper, it would be plastic. It would stick. It wouldn't breathe. So papers have to be used. And even straws. Shouldn't they be plastic? It's awful when they're paper. You're going to use more than you need. It's not sustainable because a lot of water was used in paper production. So a number of things. Everybody has their own space in the right place. And the rubber tree has a lot of appeal for that. And the forest is still standing, dripping that white milk, which is latex, for over 30 years. So what is that? 75% is water, 65% is water, 35% is rubber. And then we consider that main matrix and contributing it to to build it, to make it. On an annual basis, over 400 million tons of plastics are produced in the world every year. 50% go to landfill. 19%. So 50 contaminate the soil and the rest of the air. So it'll be incinerated, but it gets Only 9% is recycled. And 22, you don't know where it is. And they don't walk alone. So plastic can't walk to the ocean, right? So it's our fault. We do the wrong thing. So we use it a lot, and we mistreated plastics. So only 9% is recycled. And out of the 9% that's recycled, part of it can't be recycled. There are plastics that are already mixed with other plastics, and you can't separate it. And it's hard to recycle. So the only current destination is a landfill. Since our mission is to no longer have landfills, we're going to show you examples of how that may not happen. So out of the 9% that's recyclable, on average, 20% cannot be recycled and might still go to a landfill. And that involves a lot of alternatives. And so how do you go send that back to the actual automobile industry or other applications?
So, can you see this image? This in recycling is called the bottom of the tank. What is that bottom of the tank? We're going to see a video in a minute of a recycling unit. There's a conveyor belt, and people separate what's polypropylene, ABS, PET, polyethylene, and several types of plastic that has to be separated to be recycled. But there was a part there that couldn't be sorted, and it goes to the bottom of the tank because it can be contaminated with PVC and other plastics. So it goes to the bottom of the tank. And you have to pay to throw this in the landfills. And usually, this isn't informed. People say it's 5%. But when we know the owners of the industries, it can reach 30%. But it's usually 20%. It's tank bottom here. We, in sample A, 100% tank bottom. Then sample B, 90% and 10% Terpol. In C, 40% of the tank bottom, 50% of PCR, and 10% of thermal BT. And in D, 80% of recycled PC. This is very technical. I'm not going to go into details about the flow, but I would like to draw attention to something very important. The lower the fluidity, it means it's flowing better. That's not true. The equipment doesn't understand rubber. Rubber, in this test, makes it hard for the device to read it, saying that it's not flowing as well. But when we do the extrusion, it reduces extrusion and it increases the torque of the machine. So it means that the flow is higher. But the instrument doesn't read it. So we learned that sometimes the lab numbers do not really show the reality. And this is happening because the machines were made for plastic, and we put a natural rubber that is extremely resistant. I'm not going to go into the detail, but Terpol increases the flowability. So 100% of the tank bottom, this is extension. More than 1% it breaks. So we put 10 samples, and none of them went above 1 point something. Then on this one, we put 10% of Terpol. And look at where it's going. We were here with 10 of Terpol. It extended much more. So it starts becoming more resistant, more flexible because of the rubber. Then we said, well, this isn't enough. And remember, circular economy, recycling, and all that is only valid if you have money, if you have some kind of financial results. So we discovered that Terpol with recycled polypropylene improves the properties of the recycled material. So we combined 40% of the tank bottom, 50% of recycled PP, with 10% of Terpol. And this is what we achieved. And you can notice that it's very stable results. But look at what we achieved. Can you go back to the previous one? One more, please. We hadn't even reached 3. And when we have this combination of products, we went beyond 5. 5 is 4 times more than no mixture at all. And then we removed Terpol from this mix, and it went back. So the rubber inside offers flexibility and makes plastic that was lifeless. It makes it better than virgin plastic in many of the properties that it didn't have before. There are many numbers here, but what really matters of all this, look at how much it extended compared to the reference, 4 times more. So plastic is looking like rubber, even if it is plastic that didn't have any life left in it. These images show, these are microscopic images, and this was carried out at the university. We looked at the tank bottom, that mix. We injected a plate, we broke it, and on the fracture site, we analyzed 100 times, 500 times, and 1,000 times bigger. We noticed that without Terpol, there are several holes, and this makes plastic fragile. When we added Terpol, rubber covered these dark spots. So it's very visible what happened here. And on the next slide, which is the impact, resistant to impact, it means whacking the plastic to see if it breaks. When we added the best combination, which is C, 40% of the tank bottom, 50 of recycled PP, and 10 Terpol, it increased 200% the resistance to impact, because we don't have these little holes anymore. This sample is at the fracture without Terpol. It was porous. With Terpol, it wasn't porous and increased resistance. So what did we do? Of all the waste that was useless, we created a compound for our customers, and they injected this bucket. Felipe was part of the project. They injected a 75-liter bucket, 1.7 kilos of weight, using 40% of material that was going to be sent to the landfill. So we offered economics, mechanical properties, and sustainability. And now we're going to show you a video so you can rest a little from my voice. And you'll see what happened. This video is from a customer, 300 tons per month that he pays to throw in the landfill. The solution we found for them, we started with 40% of what they bought couldn't recycle and have to pay to dispose of. So the price of this raw material is negative. It's minus something. He used 10% of Terpol, 50 of PP, and this is the power of Terpol as a modifier of plastic, and not sending it to landfill. That's why automotive companies that already have high quality parts, imagine being able to get the panels, the bumpers, and grind everything together. You don't need to sort them out anymore. ABS piece parts, everything, you grind everything together. You put Terpol, a little bit of PP, and you can inject any part. And when it carries Terpol, it lasts longer. So we're starting a seed, but as Neil Armstrong would say, it's a small step, but a huge step for mankind. So we're really looking for things, showing videos of things that work. It's not just theory. This is already put into practice. And one of the hardest developments that we had to date is the roof of the car. The roof has fiberglass, PU foam, glue, textiles, PP, everything. So the world produces how many vehicles? 60 million vehicles. Imagine that each new car produced generates 700 grams of this residue, because when you have the scraps, it's about 700 grams per vehicle. So we're talking about tons from new cars alone that go to landfills. So we're working with them. This was the scrap. We created pellets and we injected a car piece. I'm not sure if this is Amarok or Hilux. I don't know if this is where it's the fender line. We did this on purpose. We didn't add any pigmentation. And these white spots are fiberglass. We injected this part without changing the setup of the injector. This part doesn't break. We checked the properties, and a pure PP resistant to impact is usually 5 kilojoules per square meter. We achieved 10 here, twice as much as the virgin material, using disposed roofs. So it is possible to find solutions to make the world a better place. Here we colored the brand, but this part was produced with recycled PP, recycled polyamides from socks. You know the socks we wear? And Terpol. And it doesn't break, it replaces ABS. Of course, for this to go into the automotive industry, it took years. So we're going for the low-hanging fruit, but it doesn't break. This hubcap is made from socks, and it doesn't break. Can you go back one more? When you use Terpol, it will increase the resistance to low temperature. Natural butter only freezes at minus 68 degrees Celsius. So it provides possibility of plastic going to slaughterhouses and other places that it couldn't go there before. This is nylon polyamide. What was the problem with this part? This part goes on the Scania trucks on the gear lever. And this is where you screw the part in the in the car's body. Nylon is very rigid. According to the strength you put, it would break the part. With in, with Terpol, we nothing broke anymore, and we don't have to hydrate it anymore. So we eliminated hydration, and we didn't have to throw away any other parts. This also is a very interesting one. This is the grill of the car. That's the most beautiful part. If you remove the grill, you'll see the radiator. It's horrible. And it's ABS plastic. When you color or you cover it in chrome, it doesn't, it breaks because the paint is an anti-adhesive. We put it in the grinder, added 8% of Terpol, re-injected, and then we painted on top of it, and it was brand new, and it doesn't break. One more solution for the automotive industry in recycled ABS.
I already mentioned the problem and the solution. In this case, we hope that someday you use this application. Last month, we had the rubber trade show. And we had a booth with an injector and a mill to grind plastic. So we launched the concept of this sneaker. This sneaker is 100% made from Terpol. So the top part is Terpol, the soles are Terpol. It's 100% Terpol. So why is it a game changer? Because the world currently disposes of 22 billion shoes in landfills every year. 3 times the world population is disposed of, and most of them with less than 1 year of use, because none of them are recyclable. Yours isn't either. None of these sneakers are recyclable because the rubber on the bottom, it's vulcanized. Can't recycle it. So depending on the upper, you can't recycle it. So we've created a completely recyclable sneaker, and at the end of its shelf life, it's going to be ground and be a plastic modifier. So at the rubber trade show, we're injecting PP plus Terpol to replace TPU. So, when we have that part, see that green part? That's polypropylene with Terpol to replace the TPU, which is thermoplastic polyurethane. 30% lighter, 100% recyclable. So in this video, you can see that we've transformed at the end of the shelf life of this sneaker into a thermoplastic modifier. Can you put up the whole screen? No? Then go back, please. little piece. I like to say God did that because it's a piece of the sewing part, the part that was sewn on the sneaker. So that's proof that it is. That's proof that it was actually made from the sneaker. So I'm almost done. I have two more videos though, for you guys. So this was injected last week during the Third Plastic trade show. This is polyester. This is the little cups of coffee. So this you could use it anymore. We added 10% of Terpol. We extruded reels 3-4 millimeters thick without any issues. We cut 800 plates and took it to the Joe and Phil trade show last week. And we showed these Ferraris at the trade show. You'll see the process, how cool it is. The PS didn't have any resistance. And then you can see the thermoforming, and that's the Ferrari. All you need is the engine and some wheels. That's another application of polystyrene that would no longer be used. And with that, you can produce a number of thermoformed parts. This is the last video. So the important thing about this video is that it was made 3 years ago when we had the idea of Terpol. This was our dream. So for 3 years, we were just testing Terpol. And this year, end of last year, we went to market. So this represents our dream. Everything is transformed in nature. It's the natural cycle of life. It's renewal. But something's out of place. We've created objects that take centuries to disappear. We use them and we throw them out. Throw them out? Plastic was a revolution. Look around you. It's even where you don't see it. Plastic can be in everything. It just cannot be in nature. We want the utility of plastic, but we do not want to pollute. We want a cleaner future, a new plastic. The plastic of the future. It's of the future because it renews itself with nature. It has life. The plastic of the future is renewable. It's recyclable. Sustainable. It is a cycle. It never dies. The plastic of the future is more flexible, resistant, and durable. It comes back and it transforms itself, and it's already a reality. The future has less plastic in nature because there's a better plastic around us. The plastic of the future. Be a part of this transformation. I would like to thank everyone for their presence. It's not easy to give a talk after lunch. Everybody's sleepy. Tried to keep you awake. Our team is here. Roberto, Richard, Carol, Philippe. In case you have any questions, any comments, they're available. Thank you for your time. Do we have any questions? We do have questions. That's great. Good afternoon. On the second slide, you mentioned applications for Terpol and you mentioned salt and pepper. Can you explain that concept that you use for salt and pepper? So it's like in kitchen, right? It's a mix. When you throw it into the funnel, it's even a paper funnel, and it's adapted. Salt and pepper means that we do not prepare the pellet. So what's a pellet? You prepare a pellet and inject. Salt and pepper is just a manual mix of the materials. And you can see the contrast between Terpol and the material you're injecting. Actually, in the injector, everything gets mixed up. The idea behind salt and pepper is that it means it could be an easy process. You don't have to pelletize to make the process. But always, if you pelletize, you get a better result. I have another question. You focused a lot on materials used with sustainable content. So materials that will naturally have degraded properties, so to speak. Do you consider the use of Terpol for prime materials? Do you have any history and application? Yes. All the work in post-consumer recycling or recyclable materials is applicable and can be reapplied. Do you have grades for the thermoplastic materials? And with Terpol? We haven't prepared PP with Terpol. Our customer will do that. Yeah, that's my doubt. But do you have a customer history that's doing that already? Yes, we do. And that's an important question. One grade isn't for everything. So there's PP grade, there's ABS grade, and there's a grade for all the different mixes or blends. Do you have a booth here? No. Maybe next time. We were at Interplastics last week, and they saw our talk last week, and they said, wow, you have to rush over and give a talk here. So they called me on Sunday so I could give a presentation here. That's great. Thank you for your question. Good afternoon. I'm Aldo from Brascan. Great presentation. You mentioned cost associated to sustainability, that it's not sustainable if there's not if you don't have the economic aspect behind that. When you do the activation, you gave some examples of applications, and 10% of Terpol and PCR recycled PP. How much would you add on to that, or the cost comparison, if you consider the 10% when you applied Terpol? Thank you for your question. That's very important. Yes, you need the economics. All the developments that come to us, the first thing is that we need to develop an economic solution that delivers mechanical properties, and after that, sustainability. So what are we looking for? We're trying to understand where customers are disposing, because that's our raw material with a negative price to justify using Terpol and its properties. So the bucket that we showed, the manufacturer can sell it 2 BRL cheaper than any other competitor. We're doing work in Dubai where plastic bags, PE plastic bags, were recycled 100% Terpol. So they were able to increase the stretching by 20% and productivity increased 8% by using 5% Terpol. So in all those cases, we're trying to transform the negative price or the productivity so that we can maintain the process standing. I'd like to add, but as a base of comparison to the PP recycled product, if you have 1 kilo of recycled PP and 900 grams plus 10 grams of Terpol, recycled PP is sold at 5-6 BRL, isn't that correct? 5 or 6 BRL. That's recycled PP. We have a number of customers for recycled PP. That's a great question, actually. So one of our customers has been buying 10 tons of Terpol, and sometimes he buys only 2 tons of Terpol. He said, I got such good PP that I don't have to put Terpol in it. But now I need urgent 5 tons of Terpol because I have to correct this waste. So Terpol will have economic efficiency if there's that type of appeal. If the PP is very good, you don't have to use it. I always like to say that we're very transparent. We're not going to push something on you if you don't need it. We're looking for solutions. There are excellent PPs that you don't have to change a thing,
And others that you do, and the quality alone of recovering it will already justify that. Sometimes 5, 8, 10, really depends. Good afternoon. Are there any studies of the relation to lowering the carbon footprint in polypropylene compounds and adding Terpol, like big numbers? So 20% Terpol, X percent decrease the carbon footprint, anything like that, just so I can have an idea? No, we don't have that yet. We want to study that on the end product because it's valid for the end product, not just the raw material. So we're starting production in Thailand next month in Terpol production because we have FSC there, and then the carbon footprint will drop a lot. So we're telling our customers that after you end development, then we study all of that. It's not just the raw material, it's everything that we're gaining in energy, lower torque, increasing the fluidity, productivity, and so on. So you have to study it on a case by case basis. The end product, of course. Any other questions? Thank you very much. Sorry I ran over. No worries. You can see how many questions you got. Thank you. Thank you, everyone.